All right, so we're on example 4. We're on example 4. And we haven't even done calculus yet. This is still reviewing logs from algebra 2, from pandemic. Look what I did. I added chords, right? So that I don't kill myself while Ben delay is charging. For g of x equals log of, right, x squared minus 3x plus 2. Find the following, okay? So first of all, we know it's a log function. We got variables in the argument, and it's log. That's a giveaway, right? Log. What's the base, though? 10, right? It's implied 10. So we don't have to write it, but you know what? It makes me feel better to have it. So I'm going to put log base 10. It says to find the domain of g of x. All right. So remember, this is a composition of a log function and a quadratic. A log function is continuous over its entire domain, and a quadratic is continuous everywhere. So when you compose two continuous functions, you're going to get another function that's continuous over its domain, right? And so that's why it's important to find the domain of g, because once we know it's continuous over a certain interval, what theorems are on our side? The what? The IVT, right? The IVT. The IVT. Okay, so how are we going to find the domain? Well, we know how to do it when the denominator is 0, right? You can't divide by 0. So you set the denominator not equal to 0. We know when we have a square root or a fourth root, the radicand has to be greater than or equal to 0. We solve that inequality. What do we do for a log? What do we know about the argument? We can only take the logs of what types of numbers? Positive numbers. Good. So we're going to show our work. We'll set the argument up, x squared minus 3x plus 2. And we're going to say it has to be strictly greater than 0. Strictly greater than 0. Now, we look at that and we ask ourselves, how do we solve that inequality? It's quadratic. Can we solve quadratic inequalities algebraically? From what you remember in pre-cal when it was inculcated into you. It rhymes with go and starts with N. No, 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 right? We can't. We can only solve linear inequalities algebraically, but even then we have to remember, right, to flip the sign when multiply or divide by a negative. So how in the heck do we solve a quadratic inequality if we can't do it algebraically? Factor. Okay, let's factor it. Does this one factor? Let's see, factors of positive 2 that add up to negative 3. 3 and negative 1.
There we go. Yes, there we go.
3 and negative 1 would give you a 4 or a 2 on the inside. Right, right. Yeah, you got your, target sum, target product backwards. All right, I'm going to revise your letter and send it back to you. Hey, did you even get the letter?
I think you emailed. I saw the email. I responded yet.
Oh, okay, okay.
I think when you send it into the college, I won't be able to see it.
Yeah, I already sent it to the college, and I saw that you said I give up the right to see it.
Okay, good to go.
Yeah, but I sent it to you in person so that you could not see it as well if you chose not to. Yeah. Okay. Now, once I have it factored, Braden said to factor it. What do? Can I then say that x minus 2 is greater than 0 or x minus 1 is greater than 0? No. No. Because that's solving it algebraically. And you can't do that. You can't do that. Okay. You can factor it and keep it fully intact. But once you split it apart, it doesn't work. Okay. But factoring it does help us find the what's of the function. The zeros, right? The roots, the x-intercepts. And once we have the x-intercepts, it'll help us sketch not a giraffe, but a giraffe, right? We should start a giraffe club here on campus, right? So let's go ahead and sketch the graph. Here's the graph. We got positive 2 and positive 1, right? They're the two roots. I guess I should move this over. We can make more use of the scale. All right, let's do this. So there we go. So there's 1 and 2. Those are the two roots, right? Positive 1, positive 2. Does this parabola open up, down, or sideways? It opens up because it's a positive x squared. So it looks something like that, something like that. That's all we really need to answer the question. We solve it graphically. Now we come back up here. For what values of x is this graph greater than 0? In relation to the x-axis, where is that? Above or below? Greater than 0?
Above.
Above, right? So remember in pre-cal, we did this all the time. It's going to either be between the x-intercepts or outside the x-intercepts. Which is it in this case?
Outside.
Outside the x-intercepts, yeah. So we would say then if we were to graph it on the line, we would say -1 can't be used because that gives us a 0, but anything smaller than 1 will work. And then we can't use 2 because it gives us a 0, but everything to the right of 2 would work. So there's the graphical solution. And now we can write it in the proper form, right? D sub G colon is the set of all x such that, and then you can say x is strictly less than 1 or x is strictly greater than 2. Okay, so for any values then that fall in those intervals, the IVT will apply. This function is now continuous on that same interval. And you could also use interval notation, right? -infinity to 1 union 2 to infinity with parentheses. Okay, can we solve quadratic inequalities algebraically? No, we have to solve them graphically, and factoring helps us. Now, just so you're convinced, right? If you were to continue with this, you get x is greater than 2 or x is greater than 1. If you were to graph that on the number line, let's do that in red. X is strictly greater than 1, that would be all this. And x is strictly greater than 2, that would be all this. You see how they go in the same direction? And the solution, this could be like the solution to some scenario, but this is incorrect. If they overlap like that, the solution would be where they overlap. It would just be everything greater than 2. So we wouldn't even need that one. So you see why it doesn't work? The inequalities don't work. All right. So you have to solve it algebraic or graphically. All right. So now that we know that, we don't really know what the graph of log of that looks like. So don't get confused with that purple graph. That's not the graph of g of x. That's just the graph of the argument. All right. Let's look at part B then. What would be the limit as x goes to 1 from the right? Oof. Well, let me go back to my little picture over here. As I approach 1 from the right, what does direct substitution give us? We never not first, right? 1 minus 3 is -2. -2 plus 2 is 0. Yeah, we know that 1 is one of the zeros. So it gives us a 0 in here. What's log of 0? Log of 0? No, it doesn't exist. Right. Okay. So this is why logs are so freaking awesome. All right. Here's what logarithmic growth looks like. Remember, you can't take log of 0. Log of 0, though, as a limit, as we approach 0, could either be what? It could be -infinity, or it could be what? Positive infinity. So how are we going to know which is which? Good question. As I approach 1 from the right, or it could be what? I'm sorry. It could also be what? If I try to approach from the side where it doesn't exist, then it would be DNE, right? Does that make sense? You could still approach a vertical asymptote from the other side, but it would not exist because there's no graph there. So this is where the graph of your inside can help. Watch this. If I want to know what the limit is from the right of 1, look at that. Can I even approach the graph from the direct right side of 1 if it's not even in the domain? No. So this has to be what? This equals DNE. Remember, if you work left to right, you put equal signs. If you work vertically, you put not equal. Do you always hold this pen like that?
No.
No? Oh, okay. I was like, yeah, mix it up. Right. All right. What would be the limit, though, from the left of 1?
Oh, now we're talking.
Now we're talking, right? If I approach from the left of 1, I'm approaching 0,
That's going down.
but it's going down. Is it -infinity?
I think.
You think?
I don't know.
Well, let's see, right? Look at the graph. My y values, when I approach 1 from the left on the graph of the argument, my y values are approaching 0, but they're still positive, right? I'm approaching from above, so it's positive. So if you take the logs of positive numbers that are really, really small, log base 10 of a positive number, This could be log base 10 right here, yes? This is the 0.10. What would be the log base 10 of a really small positive x value right here? What type of value is it? It's really negative big, right?
Yes.
Yeah. The magnitude is big, but it's negative. So what did you say the answer was? Negative infinity. And that was right. But now we know why, right? Now we know why. It's negative infinity. Okay, so notice how we don't even really need that graph. All right, what would be the limit as we approach 2 from the right? Well, 2 is the other kind of line of demarcation for the domain. If I approach 2 from the right, am I in the domain? I am. So let's think about it. As I approach 2 from the right on the inside, again, my y values are approaching 0, but they're positive. They're positive. So if I take the log base 10 of a very small positive number, second verse to the same song, isn't it? Negative infinity. Yeah, negative infinity. Now notice quickly here, if the domain had been on the inside here, right? Now as I'm approaching 0, it would be a negative number. Well, we'd have to look at the graph because then it wouldn't exist. So we're good. We're good. If the base had been different besides base 10. All right, so that takes care of those. And of course, I didn't even put 2 from the left because it's not really even a good question anymore, right? What would be the limit as we approach 2 from the left if there's no function there? D and E, right? Okay. So we can use our knowledge of what log base 10 looks like to answer these types of questions by doing the composition thing. All right, now the end behavior. This should be a little bit easier, right? What would be the limit as x goes to infinity? Well, let's look at what the inside is doing. As x goes to infinity, what is x squared minus 3x plus 2 doing? Well, you can go back to looking at the leading term again, or you can look at the graph itself, right? It's going to infinity, right? So as x goes to infinity, the inside is going to positive infinity. And now what would be log base 10 of positive infinity? Hop on the graph of log base 10 and go out forever and ever. Where are the y values going? They're still going up to infinity, right? They're still going out to infinity. Or what would be a acceptable free response answer? D and E, right? So that mantra that we kind of had earlier in the year, that maybe even I suggested, right? When in doubt, D and E, comma, but don't be in doubt, right? Yeah. And then what's the upgrade to I don't know? D and E, right? But never not know. I guess we would add that. Okay. Now, what would be the limit as x goes to negative infinity? You do it. Okay. You do it. The limit as x goes to negative infinity. And don't just say D and E because you don't want to think. Right. Remember, if you work left to right, you need equal signs. You have them here. Yeah. If you work straight down, you don't need them. Do what? Do Did you put D and E without thinking?
No,
You need to put equal signs in between them. Remember, if you work left to right. Yeah, a lot of people. Yeah, if you're working left to right, you need equal signs. If you work straight down, which I didn't leave room for that, then you don't need equal signs. So practice the way we're going to play. All right. I see a couple of answers and then or DNE. Nice. Okay. If math were a democracy, okay, good. If math were a democracy, which it is sometimes, right? Not really. But you can make people think it is. The answer would be, is it D&E because the graph doesn't exist there, or is it D&E because it's some type of infinity? Because if it's some type of infinity, let's try to put that on there too, and then or D&E. Oh, okay. All right. Oh, wow. Okay. Uh-oh. Actually, this is starting to look kind of not anonymous, but unanimous, right? I see a lot of infinities going on. Now let's see if that's correct. How would you analyze it? The limit as x goes to negative infinity. Again, you analyze the inside first, it's x squared. What does x squared do as x goes to negative infinity? In other words, what's negative infinity squared? Positive infinity, right? And now what's log base 10 of positive infinity? Infinity, right? And you can also look at this graph right here. The left-hand behavior of the argument is positive infinity, and then log base 10 of positive infinity, okay? So it is infinity, y'all are correct, or DNE. Now, look at what I did on part D. And this is kind of what I was trying to say on part A, but then I shut myself up because I realized what I was doing. We'll have to do this quickly. What would all the answers to the above be if the function were log base 0.1? What is 0.1? Is that log growth or decay? It's decay because it's less than 1. So we'll just say this would look like this. And now the graph looks like this. So all of the answers above that were positive infinity will turn into negative infinity, right? And yeah, would it be all of them, or would it just be on part C? The inside, notice real quickly, the inside stays the same. The inside stays the same. So let's just do real quickly, let's do B2 again. If I approach 1 from the left, it's still this graph, right? Approaching 1 from the left is still approaching 0 from the positive side. But now if I take log base 0.1 of a small positive number, it's going to be what type of number? Big positive number. So yes, it'll change all of these. So real quickly, y'all can kind of stand up and walk out. All infinities change signs. Okay. The one that was D and E, because it doesn't exist, unfortunately, there's no help for the base making it exist. So it's still going to be D and E. Okay. So when we get back, we're one example closer to BOTCing. Okay. One step closer.